All right, friends, we're back and we are almost there. This is 12.2, which is nearly the end of chapter 12. And if you're looking at the CED, this is the end of Unit 8. Unit 9 is the end. And that's all she wrote. Now, part of me is a little sad that this is the very end of the course because, I could imagine us kind of trying to shove our way through the rest of this curriculum, but I really, really like this chapter and I think it's really interesting. So I'm kind of hoping we can, at the very least, come back and look at it more as we get ready for the exam or, maybe in future years, spend a little more time on it. Okay, so today we're going to be talking about a few different things, tests for homogeneity and also tests for independence. This is a really big lesson as far as time and how long it's going to take me to get through it. So let's get to it. So, does background music influence what customers buy? One experiment in a European restaurant compared three randomly assigned treatments: no music, French accordion music in the background, and Italian string music. Under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. So, the null hypothesis in this case would be that there's no difference in the true distributions of entree orders at this restaurant, whether there's no music, French accordion music, or Italian string music. And the alternative hypothesis is that there is a difference in the true distribution of entrees that were ordered under these circumstances. So the alternative hypothesis this time does not state that each distribution is different from the others, just that there is a difference this time. So here's our data put into a lovely table. And then they also graph some not histograms, bar charts down here, or frequency charts, if you want to call them that. So they're separating here the no music versus French music versus Italian music, and then the different types of entrees that were ordered in those instances. So, do the differences in the distributions provide convincing evidence that the background music affects customer behavior at this restaurant? Or is it plausible that the background music has no effect on customer behavior and that these differences are just due to the chance involved in random assignment and treatments? So that is always the question, right? And that kind of leads us to believe we're going to be doing a full statistical analysis, which we will eventually. So for now, we're going to start slow. And they're going to talk about what are your options. So we could compare many pairs of proportions and have a whole bunch of tests and many different p-values, which would be a little overwhelming. Also, it's just bad stats because the more tests that you run, the more probability you are to have a type 1 error because, you're going to have that chance every time you run a test. So the problem of how to do many comparisons all at once without increasing the overall probability of a type 1 error, and they give you a couple of methods for doing this. So 2 steps. First step, perform an overall test to see if there's convincing evidence of any difference among the parameters that we want to compare. And then when the overall test does show that there's convincing evidence of a difference, follow it up with a follow-up analysis and decide which of the parameters differ and to estimate how large the differences are. Sounds a little complicated. All right, let's take a look at it. So first we got to do find the expected counts. And there's a wonderful video from, I think it's from Luke Wilcox on the AP Classroom website, and it's called like how to calculate expected counts or something like that, right in the middle of the unit 8. So I really suggest you watch that because I think his shortcut method is beautiful, and I think we're going to be using that in our class as well. But for here in the notes, just to kind of stay consistent with what you're going to see, they first assume that the null hypothesis is true, which is what we do with testing, so that makes sense. So as you look at that, if the specific type of music that's playing has no effect on the entree order, then the proportion of French entrees should be equivalent to 99 out of 243. So it should be equivalent to that proportion, which is about 41%. So as you look through your table, these are the observed values, but if we were to calculate expected counts, and then they continue on. Because there's 84 total entrees ordered when no music was playing, we would expect 84 times that proportion of French entrees on average. So what they're going to show you now is how do you actually calculate all of these, and notice now here they have what are called expected counts. Well, there's a shortcut that they claim is really easy, but like I said, Mr. Wilcox has a really good video up on AP Classroom I think you should watch. So they say just take the row total and the column total and divide it by the table total. Oops, there we go. So you'll see what they did there. So how did they find this 34.22 is how they described it on the last slide. So they said they know it's going to be in a ratio of 99 over 243. That's where this red over blue thing is coming from. But then you got to multiply it by the column total to figure out the actual number of French entrees that you expected to be ordered. Now, this is again on average, so you want to not round to the whole number this time like we did before. And you're going to have to do that for every one of those rows in theory. But like I said, Mr. Wilcox's video shows you how to kind of shortcut that. You really only need to find a few of them, and then you can figure out the rest just simply by subtracting. So kind of backing up here, in class, we'll go over like, okay, I should find this one and this one and this one. And once I find these, then I should be able to find the rest just simply through subtraction because you know they have to add up to 84 in this column and so on and so on. We'll talk about it. All right, as with chi-squared tests for goodness of fit, the expected counts should not be rounded to the nearest whole number. While an observed count of entrees must be a whole number, the expected count is like an on average kind of a number, so you shouldn't be rounding it that much. And you want to make sure that your data is good, so don't round off too much. Chi-square statistic looks familiar, right? It's the sum of all the observed counts minus the expected count squared divided by the expected count. So the sum is over all cells, not including the totals. And I've caught myself getting in trouble here because sometimes I get a little happy with my formulas and I start calculating expected counts where they shouldn't belong. So be careful. So this is that French, the various types of music versus what entree was ordered example, I believe. And they calculated it. And yep, they're doing it by hand, which looks fun. We'll talk about the calculator later. Oh, that's so funny. I never caught on to that. We will talk about the calculator options of how you can find this. It involves a matrix, so it's pretty fun. So in the do step, you aren't required to show every term in the statistic. So they suggest you write the first couple and then dot, 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 and then the last one. And then same thing as you go through your work. And remember your calculator, yes, can help you, but we'll talk about that later. Let's see. So we have a new problem here for our class project. Abby and Mia wanted to know if the gender of an interviewer could affect the responses to a survey question. So the subjects in their experiment were 100 males from their school. Half of the males were randomly assigned to be asked, would you vote for a female president? By a female interviewer, and the other half were asked the same question, but by a male interviewer. So the table shows the results. So here's our two-way table, which tells us that we need to be comparing our categorical data. And we're going to be asked to state the hypotheses, show the calculations for the expected counts, and then complete the table for expected counts. Oh, and they just want us to show the calculations in one of the cells. And then calculate the value for the chi-square test statistic. So starting with the hypotheses. Ugh, that's a lot of words. So basically the null is always there's no difference and the alternative is that there is a difference. So there's the null hypothesis being that there's no difference in the true distributions of response to this question when asked by a male interviewer versus a female interviewer. And they slid in that for subjects like these because we know we're supposed to say something to that effect when we are running a test on an experiment. And then the alternative was the same idea, except it states that there is a difference. So for the expected count specifically for male, yes. So we're talking about this observed value of 30, but what's the expected count? So what they did was they took the ratio of yeses over total, so 0.69, and that was what they would expect to see if the null hypothesis was true. And if you took 0.69 and multiplied it by 50, that's where they're getting this 34.5 for the expected result. They just use that cute formula, but I'm not real big on formulas. I always have to think about where they're coming from because I have a really hard time remembering formulas, especially if I have a chance of getting it backwards. And then the rest of the expected counts are shown for you for male and female, yes, no, and maybe. And remember, you don't have to calculate each of them because remember this row has to add up to 69. So 34.5, if you took that away from 69, you'd get that. And then so on and so on for some of the other values. They could have kind of not cheated, but found them a little easier. Now for the chi-square statistic, they're taking the observed minus the expected, squaring them and dividing by the expected. And then they're adding up all those values and they're doing the cute dot, dot, dot thing because no one wants to do that all. And then it comes out to 4.25. And we're going to learn next how we can then take that and actually perform the test itself. So, oh my gosh, I love this question. I think they've brought it back since, I feel like we saw this in chapter 1. Separate random samples of children from the UK and the United States completed a survey, and they asked them what kind of superpower would they like. So they gave them some choices, and they want to know if we have convincing evidence that the distributions of superpower preference are different for survey takers in the two countries. So we have a two-way table of some categorical data, a good indicator that we're going to be using a chi-square test. And earlier in the year, we saw this question and we just kind of were asked, is there an association? I think the word was brought up. You know, can you tell a difference between the countries? We asked him in very, I won't say layman, but like early on in our statistical journey kind of terms, like things that you probably could have answered before you even took the stats class. So now we're going to talk about how we formally answer that question. So we're going to state the hypotheses, we're going to show a calculation for an expected count, and then obviously fill in all the rest, and then go ahead and calculate the value for the chi-square statistic. So answers are coming your way, so pause the video if you want to try this one on your own. The null hypothesis is that there's no difference in the true distributions of superpower preference between UK and US, and the alternative is that there is a difference. So calculating the expected count for, they wanted UK and fly. So what they did was, here's UK and fly. This is the observed count. So they took the 99 out of 415 ratio, and they said, okay, whatever percent that is, how many of these 200 would have said that? So 99 times 200 divided by 415 is how they calculated. Spoiler alert, it's 47.711. I feel like yeah, that's right. I'm trusting you, book. So then they did that same calculation, but remember, you don't have to do it for each individual like cell here, because once you find a couple, like for instance, the UK, you can find the US through subtraction. You could have done that a few different ways. And then the chi-square statistic is a hoot. So 54 minus the expected that you just found, square that, divided by that expected, and you had to do that for each individual one, and it was a good time. And then you added them up, and you got 6.29. Now, is this super fun to do by hand? Heck no! So we will be showing you calculator work soon. All right. So test for homogeneity, and then going through the conditions and, actually calculating p-values. That's our next step. Oh, look, the same 3 conditions as always. Now remember, for chi-square, all expected counts have to be at least 5. So here we have that interviewer gender question where half of the men were interviewed by a female interviewer and the other half were interviewed by a male viewer. And they put their data into a two-way table. And then you're seeing here the observed counts versus the expected counts. And these were already calculated earlier in our journey in this lesson. We also calculated a chi-square statistic of 4.25. So, excuse me, verifying that the conditions are met for inference. Well, it was a random selection, or sorry, not a selection, but a random assignment, because remember this was an experiment. So the treatments were randomly assigned. So whether this particular person was getting a male or female interviewer was randomized. All the expected counts are at least 5, because I can see that on the table. And then you don't need to worry about the 10% condition because we weren't randomly sampling. These were volunteers, I believe. I forgot how the premise of this problem looked, but we don't have to check 10%. To use table C to find the p-value, cool. I don't want to do that, but I will. And then use your calculator's chi-square CDF command. So using table C, you have to first find the degrees of freedom. So remember, you take the number of rows and columns, subtract 1, multiply them together, and you get degrees of freedom of 2. So then you go to that row on table C, and you see that that chi-square statistic is going to fall between 10 and 15%. Now, that same idea, but using the chi-square CDF command, remember chi-square always reads to the right. So that came out to specifically 11.9%, which follows along with us thinking it was between 10 and 15, so that feels good. And now we can actually interpret the p-value. And guess what? It's the same way we interpreted it before. So the p-value from the calculator, more specifically, we're going to assume that the gender of the interviewer doesn't affect the responses. Remember, the first thing you do when you interpret p-value is you assume the null hypothesis is true. So that means there's like a 12% probability of getting the differences of the distributions of responses as large or larger than we saw in the study just by chance alone. So you've got a pretty significant probability of getting that result by chance. And that's what allows us to make a conclusion. So because the p-value is about 12%, which is bigger than our significance level of 5%, we failed to reject the null. There is not convincing evidence that a difference in the true distributions of responses when asked by a male versus female interviewer. And then again, they snuck in that for subjects like these. So it's nice when things kind of come together, huh? All right, I promise you calculator, I show you calculator. As usual, technology saves time and gets the arithmetic right. Heck yeah, it does. So I'm going to be honest, as much as I love chi-square calculations, I probably won't be doing them by hand. And I'm fingers crossed, maybe we'll have the opportunity to do some by hand, but hopefully we won't have to. But this is what we're going to have to do. The first thing you have to do is you take your observed counts and you enter them into matrix A. So if you've never worked with a matrix before, up here, this is called the dimensions. And matrix is found in the matrix button, by the way. It's on the, oh boy, I don't have a calculator in front of me, but it's on the left side, shift something. Anyways, it says matrix, can't miss it. So when you choose matrix A and you edit it, this is rows by columns. So it's number of rows and number of columns. And you want to enter not the totals, notice, just like the body of the two-way table. So enter all those observed counts. And then when you go to your favorite menu for tests, which is the stat test menu, you're going to see something called chi-square test. And I know it looks confusing because you're like, wait, expected B, I didn't put anything in B. That's okay. Your calculator's going to do that part. So observed data goes in A. Don't worry about B. It's just where it's going to be put. And then you're going to hit calculate. And your calculator is going to say, hey, here's your chi-square statistic, here's your p-value, and your degrees of freedom, by the way, are also 4, which you would have to write down. Now, if you actually open up matrix B, you're going to see all of those expected values that we had to hand calculate done for you. So those previous questions, they straight up asked us, like, show your work on how you found one of these cells. I don't know if they're going to make you do that on a free response, but I could see that forming as a multiple choice question, like which of the following is the correct calculation for finding the expected count for this? So we do have to kind of remember that formula a little bit, but I really prefer just to think about how it's calculated. But this is the good news, guys. You don't have to find all those expected counts by hand. Yay! Now they're going to give you a tip about using your calculator. You can use your calculator to carry out the mechanics of a significance test, any kind, right? But there's always risk involved. If you do the calculator method and you type anything in wrong, so if like you did the matrix stuff and you typed in, 3 instead of 30, I do that a lot where I leave a 0 off, your whole step is going to be wrong, like the whole thing. So we recommend writing out the first two terms, and then dot dot dot, and then maybe the last one if you're into that. At least you'll get partial credit if you did something wrong, other than just losing all credit for it. And if you choose to use the calculator strictly, just make sure you definitely report the statistic, the degrees of freedom, and the p-value. So, the superhero problem's back, and this time we are going to verify the conditions. They want you to go old school and find p-value on table C and then also on your calculator. Interpret your p-value, which remember we start with assuming the null hypothesis is true, and then actually make a conclusion. So pause your video because the answers are about to be shown. So they were random sample of 200 survey takers from the UK and 215 from the US, so check, check. The 10% condition, it's reasonable to say that 200 is less than 10% of all, I think it was school-aged children, so yeah, in the UK, and then same thing for the US, 215. All the expected counts are at least 5. I believe we calculated that in a previous part of the video. And if not, we probably could have used our calculator real quick to find that, right? Putting in matrix A. Now the test statistic, 6.29, that's coming off the calculator. And then, well, not necessarily. I guess they could have done it by hand. They didn't show any work on finding that. I think we did that earlier in the video, now that I say that. The degrees of freedom, there, let's talk about that. 5 minus 1 is 4, 2 minus 1 is 1, 4 times 1 is 4. So here's our chi-square distribution with degrees of freedom of 4. And they've drawn a very beautiful picture. I can promise mine wouldn't be that pretty. But they've marked a statistic of 6.29, and then obviously chi-square is always greater than, so it always goes to the top. So using table C, when you're in the degrees of freedom row of 4, you're going to see your p-values between 15 and 20%, and using technology, it's about 17 point, well, it's exactly 17.85%. So the conclusion, I don't know if they set up a significance level. Oh, sorry, not the conclusion yet. We got to interpret. So, assuming that the distribution of superpower preference is the same for UK and US children, I believe it was, there's a 17.85% probability of observing those differences as large as we saw, or even larger, by chance alone. So that's a really high probability, and that's why we fail to reject the null hypothesis. We do not have convincing evidence that there's a difference in the true distributions of superpower preference when you compare the US to the UK. All right, so here is the wonderful putting it all together moment. So we're going to go through like the entirety of doing a chi-square test for homogeneity, and they're going to give you all the information you need right here. So talking about the null hypothesis, stating that there's no difference, and then the alternative hypothesis stating that there is a difference. The chi-square statistic is the same as it always was. We just got to make sure that we sum over all the cells but don't include the totals like I would. And then we're going to find the p-value for the upper tail of a chi-square density curve. And then we're going to find degrees of freedom by taking rows minus 1 and multiplying that by columns minus 1. You know, just a little of that. All right, so the Pew Research Center conducts surveys about a variety of topics in many different countries. And in one survey, it wanted to investigate how residents of different countries feel about the importance of speaking a national language. Separate random samples of residents in Australia, the United Kingdom, United States were asked many questions, including the following. Some people say that the following things are important for being truly, and then survey country nationality is put in place there. So others say that they are not important. How do you think it is? Sorry, how do you think it is able? Wait, what? How important do you think it is able to speak English? Oh my gosh, apparently this American cannot read English, so there we go. The two-way table summarizes the responses to this question, and do the data provide convincing evidence at the 5% level that the distributions of opinion about speaking English differ for the residents of Australia, UK, US? Well, all right. So there's your ladies' data. That's what I was looking for. This whole problem just made my brain hurt. And it is definitely a two-way table. We have multiple categorical variables here. So we are going to be performing some type of a chi-square test. The title tells me it's for homogeneity. We'll talk more about other types in a moment. And we got to go through the gamut of the significance test. So first things first, we're going to need to state what we're trying to do. So the alternative hypothesis is that there's no difference in the true distributions of opinion about speaking English for residents of the 3 different countries that were interviewed. And then the alternative is that there is a difference in the true distributions of opinion about speaking English for all those 3 countries. And we're going to use a 5% significance level. So next, we need to check our conditions. These were independent random samples from the 3 countries. 1,000 is less than 10% of all Australians, and so on for the other countries. And then you can see in a moment that all the expected counts are greater than or equal to 5. Speaking of expected counts, however you found these expected counts, they're wonderful. And remember, it's just for the body of it right here. So just kind of going through one calculation, if you're not sure where they got this number from, it's possible you could have used your calculator using matrix A and then performed a chi-square test. And it would input this expected count into matrix B. But the other way to get this 741.8 is to figure out the percent that should have said very important. So 2569 divided by 3463 and then multiply that percent by this 1,000 people that were interviewed from Australia. And that's where the 741.8 came from. And they would have kind of continued on with that idea. For UK, it would have been this divided by this times the 1460. That's where the 1,083 came from. And then after that, after you got a few filled in, you could do some subtraction. Good times, right? I'm gonna be honest, guys. If this was on a free response question, I think I might just like let the chances go in my favor and use my calculator because I just do not foresee me calculating everything right, and I'm gonna lose so much time. And I'm pretty sure I can triple check my typing to make sure I get that part right. I'm gonna be honest. All right, so we're on the do step, and we're taking the observed minus the expected, squaring that, and then dividing by the expected. And we're going to do that for all of the um, variable components here, not the totals, but the body of the table. And we get a chi-square statistic of 68.57. Now the degrees of freedom, rows -1, columns -1, multiply them together, you get a 6. So if you're going old school and using a p-value, table C to find a p-value, you're getting something incredibly small. And if you're using technology, you're getting essentially a 0. That, my friends, isn't a very small p-value, and it's definitely less than alpha, so we reject the null hypothesis. There is convincing evidence that there's a difference in the true distributions of opinion about speaking English for residents of Australia versus UK versus US. I'm going to be honest, I probably was going to bank on that as being a difference. That's the way my gut was telling me to go, but at least now we have the statistical evidence. All right. Many students will lose credit on the exam because they don't write down and label the expected counts in their response. It's not enough to claim that all the expected counts are at least 5. You have to show clear evidence. So right here, and you don't necessarily have to make a new table. You can, if you have room, this one's pretty small. You could have snuck the expected counts in the cells themselves, and I think that's probably the easiest way to do it. And you'll notice your book often puts them in parentheses inside the table. I think that would be enough to give you credit. All right, so here we have a check your understanding problem. So it's about Canada having universal health care. The United States does not, but offers more elaborate treatments to patients who have access. How did two systems compare in treating heart attacks specifically? So researchers compared random samples of US and Canadian heart attack patients, and one key outcome was the patient's own assessment of their quality of life relative to what it had been before the heart attack. So here's the data, and we do have a table, and it's looking good. So they want us to find is there significant evidence between the two distributions of quality of life ratings for Canada versus US? And they want us to test at the 1% significance level. So pause the video and see if you can carry yourself through a significance test and see where you get stuck. All right, answers coming next. So our null hypothesis is that there's no difference in the true distributions of quality of life for patients who have suffered a heart attack in the Canada versus US, and the alternative is that there is a difference. 1% significance level. Here's our plan, guys. A chi-square test for homogeneity, checking your 3 conditions. They're both independent random samples. The 10% condition looks reasonable, and large counts. As shown in the table, which you would have to write down somewhere, all the expected counts are at least 5. So then, actually performing the chi-square test, this is a by hand approach, obviously. They're showing the calculations for how to find this value. In all likelihood, I might jot that down and definitely use my calculator to find these values. The degrees of freedom, you don't have to show the calculations, but you do have to note that they are 4. And then for our chi-square test statistic, 11.725 and above, calculating that p-value, of course, we're all going to use technology. Ooh, now on a normal day, that would have been a good p-value, but this is 1.95%, and they wanted the 1% level. So because our p-value is greater than alpha, we fail to reject the null. There is not convincing evidence that there is a difference in the distribution of quality of life for heart attack patients in Canada and the United States. Well, that was fun. All right, so I think we're about halfway through the lesson, if you could believe it. It's a long one, I warned you. And now we're going to consider a different type of relationship between two categorical variables. So are people who are prone to sudden anger more likely to develop heart disease? We have an observational study of a random sample of 8,474 people with normal blood pressure for about 4 years. Each person took the Spielberger Trait Anger Scale test. I think that's a thing. Oh man. All right. Researchers also recorded whether each individual developed coronary heart disease. That I do know is a thing. I should go take the Spielberger Trait Anger test scale test. Oh man. All right. Maybe like take it in August and take it in May and see if it changes. Sounds like a different study. All right. So here's their data in a two-way table, and they also showed you a barb chart over there. So low, moderate, and high anger levels, and then whether they developed heart disease or not. So do these data provide evidence of an association, and this is an old word that's coming back, between the variables in the larger population? So are you more likely to have coronary heart disease if you have a certain level of anger is what they're going towards. So in these cases, and what we're going to call these, this is a test for independence. Okay, so it's not homogeneity anymore. This is a test for independence. Trying to see if there's an association between the variables. So the null hypothesis is that there's no association between those two variables, the anger level and the heart disease status, for people that were in the study. And then the alternative hypothesis is that there is an association. So the hypotheses are not really like rocket science here, guys. It's just the only thing that's weird about this one is the null is that there's no association. Um, in other words, saying that they are independent from one another. So here you go. Another way to say it is that anger and heart disease are independent, and the alternative would be anger and heart disease are not independent. That's what you're really testing. So, very similar to homogeneity calculations, if we choose one of these people at random who said yes, that in our data was 190 out of the 8,474 people. So if we assume the null hypothesis is true, then the anger level and the coronary heart disease status should be independent from one another. So very similar for expected count calculations. You should be able to calculate them based on the null hypothesis. So here what you see is the probability that someone, yes, developed heart disease given that they have low anger. So 190 out of 8,474 is roughly 2.2%. And you would expect that same number to happen with this total of 3,110. So, okay, they did that for you. This 53 from the observed data is a bit far off from our expected count here of 69.73. So you might notice how they're calculating these expected counts is very similar to how we did earlier in the lesson for the homogeneity test. In fact, it's exactly the same. Okay, so you might be wondering, oh, can I use my calculator to find these? And the answer is yes, you can. We know the risk of using a calculator, but for me personally, it's worth it. Conditions for performing a chi-square test for independence. Still random samples from a population of interest. Still matching the 10% condition if you are sampling without replacement. And large counts, all the expected counts must be at least 5. Sounds familiar, right? Hey, look at that. Looks almost the same. The only thing difference here, guys, is how they set up the hypotheses and what you're actually testing, like the point of the test. So nothing new there. So let's talk about, oh, I love how they're already putting it all together for you. Because you know what? It's really the same. It's a different hypothesis. So it's the same idea, though. So, oh my gosh, the snowmobile question is back. I love this question. We saw it like every single chapter for a while. So we have snowmobile experience compared to environmental club status, being a member or not. And first question, actually the only question, do the data provide convincing evidence that there's an association between being an environmental club member and your status on whether you've used or rented or owned a snowmobile? So we're going to go through the 4-step process. We're going to state first in the null hypothesis that there's no association between being an environmental club status, a member, excuse me, and then the type of snowmobile use. That's a lot of words. I feel like they worded that up way too much. And then the alternative is that there's no association between those two things. So 5% significance level. Now, had you used the words independent and not independent, that would have been fine as well. Chi-square test for independence this time. Random sample, check, 10%, sounds good. And then large counts, we're going to see in a minute, all the expected counts are greater than 5. Speaking of expected counts, here they are. Remember, if you're wondering where they found these numbers, for like this not a member never used a snowmobile, they would have taken the never used a snowmobile proportion, so 657 out of 1526, whatever decimal that was, and multiplied it by 1221, and that's the expected count for this box. That's where the 525.7 is coming from. Again, they could have used some fun on the calculator and got the expected counts in the matrix. So, they did the chi-square statistic calculation here by hand, or at least they fudged it in pretending they were doing it by hand. I like that. 116.6, that seems awfully large. So then the degrees of freedom are either calculated if you're using table C, or if you're using the calculator, it'll give it to you. And then using the chi-square test, so that same test feature we used earlier in the in the section, we're using that same one. You get like almost a zero. Can we just call it a zero, guys? 0.025 times 4. Like, come on, y'all, that's zero. Because the p-value is so incredibly small and very far less than 5%, we can reject the null hypothesis. We have convincing evidence that there is an association between the environmental club status of their membership versus the types of snowmobile usage for these people in visiting Yellowstone in the winter. And we already knew there was an association way back in chapter 1, but now we're using statistical inference processes to show that there's an association without the shadow of a doubt. All right, when the p-value is very small, like we just saw that, the calculator will report it using scientific notation. So just be careful that you're not just looking at the beginning of it. And like I have a lot of kids who would have read that as 4.82, which doesn't make any sense. That's like 482%. So you really have to think about like opening your eyeballs a little bit, guys, and watching out for scientific notation when it comes in. Plus, if you remember when we got that chi-square statistic and it was like 116.6. Now, I realize all chi-square distributions are different between the degrees of freedom, but I think we can all agree that we have never seen a statistic that far out on the curve. So you knew it was really far out. So you knew it was going to be 0 for p-value. I mean, I say that, but whatever. I'm assuming you knew that. All right, so we're checking our understanding. Pause the video in a moment. If you don't want to see the answers yet and you want to try this on your own, we have a random sample of 1,200 U.S. college students and said, what is your perception of your own body? Do you feel you're overweight, underweight, or about right? And here's our two-way table and then separated by binary genders. Do we have convincing evidence at the 1% level of association between gender and perceived body image? I wonder how this one's going to end. Let's find out. All right, so null hypothesis is that they are independent, meaning gender and perceived body image. You can also say there's no association. And the alternative is that there is an association or that they are not independent. And we're going to test at the 1% significance level. We're performing a chi-square test for independence, checking your 3 conditions. Both samples, whoops, sorry about that, if you could hear that. Both samples were random. Well, I should say the sample was random. 10%, 1,200 is less than 10% of all college-age students, and all the expected counts came out to at least 5, which they probably hand calculated because they're a little extra. If we're doing this on the calculator, we could have used a little bit of technological help for sure. Now, be a good soldier and pretend like you're doing this one by hand. So observed minus expected squared divided by expected. Add them all up, or at least pretend you did, and you're going to get a chi-square statistic of 47.176, which is pretty far out there, so we'll see what that p-value comes out to right now. No crazy people here. We're not using table C. So use technology, chi-square CDF, lower bound, upper bound, and it's possible you just did a chi-square test. I get you. And it essentially comes out to 0, guys. So this is your p-value, 0. Because we have a p-value of basically 0, and that's definitely less than 1%. We reject the null hypothesis. There is convincing evidence that there's an association between gender and perceived body image in the population of the U.S. college students. Huh, who would have thought? Gee, I wonder which direction it was going. All right, so chi-square test versus homogeneity and chi-square test for independence are very similar. In fact, they even use a lot of the same calculator triggers, which confuses kids because they're like, wait, what am I doing? What is it? Is it this one? Is it that one? Because it's the same thing on my calculator. So the best way to distinguish between the two tests is to consider how the data were produced. This is very similar to when we talked about like difference in means and mean difference. Like think about what your data is trying to do. So if the data come from 2 or more independent random samples, then you have what's called a chi-square test for homogeneity. This is also true if you had different groups in a randomized experiment. So they have to come from 2 different places for homogeneity. And if the data comes from a single sample and you're trying to classify between 2 different variables, this is a chi-square test for independence. You'll often see that question phrased as something like, do the data provide convincing evidence that there's an association between these 2 things? That's usually what I look for a chi-square test for independence. So here, sorry about that. Phone's going off. Don't worry, it's just my mother. I'm old and I still get called by my mother all the time. Are men and women equally likely to suffer lingering fear from watching scary movies as children? Yes, we're terrified. Researchers asked a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. Oops. The following table breaks down these results by gender. Assuming that the conditions for performing inference are met, then we're going to have a mini tab output for chi-square tests using the data shown. Now this is an interesting twist on the problem, and this is something I could definitely see on an FRQ or something else coming up, because they know that you could just crank stuff away in the calculator, and they're wondering if you can actually interpret it. That's what the point of these questions are. So the first question is, do we have a test for independence or for homogeneity? And you have to kind of justify which one it is. So we have a test for independence. We have data coming from a single sample of college students, and they're trying to differentiate between gender and whether or not, we have, what did they call it? Lingering fright symptoms. If it was a test for homogeneity, you would have to have 2 different independent random samples from each population, comparing 2 different samples. So state an appropriate pair of hypotheses for researchers to test in this setting. So this is where we're looking for an association or not. So the null is that there's no association between gender and whether they had lingering fright symptoms. And then the alternative is that there is an association between those 2. Which cell contributes most to the chi-square test statistic? So I like this because they went ahead and kind of showed you all the breakdown of the data from Minitab. And if you read it carefully at the top, it says expected counts are printed below the observed counts. So like for male, yes, this is the observed 7, but we expected it to be 11.69 if there was no association. And then for female, the observed was 29, and we expected it to be 24 if there's no association. So then the numbers underneath that would be your contributions, I'm assuming. So men who admit to having lingering fright symptoms account for the largest component of the chi-square test statistic. Yeah, that's the contribution. So you notice the 1.883 and the 0.906, and then these guys. So he's the biggest one. Far fewer men in the sample admitted to lingering fright symptoms than we expected if the null hypothesis were true. So 7's what actually happened in the observed data, but if everything was true and true to form for the null hypothesis, meaning there's no association, then we should have had, about 12, and we did not. So we're going to interpret that p-value, which is clearly labeled down here in the corner, and then eventually make a conclusion. So remember, when you interpret a p-value, you assume that the null hypothesis is true. So if there is no association between gender and whether or not they have lingering fright symptoms, there's a 4.5% probability of getting that strong or even stronger data than what we observed in the 117 students. Now, our p-value is greater than our significance level, so we fail to reject the null hypothesis. We do not have convincing evidence that there's an association between gender and whether or not college students do have lingering fright symptoms. Oh, that was the end. So before I end the video, just kind of one final thought about that. So I could foresee a few things happening in this chapter where that might trip some kids up. The calculation is kind of a beast, so I'm definitely going to be playing with my calculator quite a bit here. I feel that's the way I would do it. The process, the four-step process is not different, but I think the thing that might be tricky is deciding between, chi-square test for homogeneity versus chi-square test for independence. And then, like they showed in this example, if you have data coming from one sample, that's a test for independence. If you have data coming from two separate samples, two independent separate samples, that would be a test for homogeneity. All right, that's that. One more section and we are done. Good luck.